done one of these before?
No. How about you?
Good afternoon, everybody.
Used to.
Welcome. I'm Rob Penzer. I'm the Associate Director of the Helix Center. Have an announcement for an upcoming roundtable on Saturday, May 20th on complexity and emergence. It's the second of our roundtables on the subject, called Visions of Cosmic Order from Particles to People. And our discussants will be William Grassi, who's the founder of MetaNexus, David Grinspoon, Senior Scientist at the Planetary Science Institute, Ilya Temkin, Professor of Biology at Northern Virginia Community College and Research Associate at the National Museum of Natural History, and Tyler Volk, Professor of Biology and Environmental Studies at NYU. So today's topic, design and nature. Let me introduce our participants today, and when I announce your name, if you can raise your hand. Elizabeth Alter, Adrian Bejan, Robin Collins, Mark Norell, and Caleb Scharf. And without further ado, I turn this over to our participants.
Go ahead. You're looking at me. Go for it. Okay, well, I guess we're talking about design and nature. And, design and nature has always been one of these things that people have questioned since the origins of modern science, especially in Western Europe and things with the origin of the Enlightening. And, design and nature can be boiled down into two different things. One, is there a creator? Is there some intelligent being who figured all this stuff out? Or are we just the products of physical constraint? I mean, is it the reason that knees look like hinges is because that's the way it works? Is the reason that we have so many of the same kinds of eyes and everything from giant squids to ourselves, is that just because of things that are embedded within our developmental patterns in our DNA, and with evolution being an optimizing criteria, an optimizing process, that's just what ends up under different selective regimes. So this has always been two different kinds of things which people have looked at. Myself, I'm more on the kind of I'm just a replicating piece of DNA, and this is just the way that it works out as far as the way that we deal with the world, either through constraint. When I say constraint, it's either through physical constraints from the external part or through constraints just on the basis of that our genetic material is possible to be able to do within certain kinds of things, along with our developmental channeling. But, some other people have some different opinions, so let's open it up.
I would see that as not, you kind of painted those two as contraries, but you might ask about the constraints themselves, whether there's a design-like pattern in those constraints. And so you could have it, and you have to look at reality, physical reality, in different levels. You've got the biological level down to the chemical level, and the biological level seems to be, at least a lot of accidents seems to be the one of the governing principles. But when you get all the way down to, let's say, the physical level, that's where I think a real big question comes in. To what degree does that look random, or is that have a design-like character? And by design in a very general sense, I would say that the parts, so you can invoke a creator, but I think there's even a more general sense in which the parts are arranged in some intricate way so that they realize some easily recognizable overall property. And so in the case of, like, I work in the area of, fine-tuning of the cosmos for life, and so there things do seem to be extremely well adjusted so that life can exist.
I would disagree.
Go ahead.
No, you go ahead and then come back.
Well, I get it. I know this understanding of design, as you stated it, but it is a novelty because English is, in fact, a very, very young language. Design is a very old concept. It comes from Latin. The word signum means sign. It is something that's discernible, meaning to us, the observers, and this observation, the sign, conveys a message which, if followed, it means that it is useful to us. Engineering, which is my education, comes from that. It is about, making better drawings. And so That's design. And where the image comes from, for example, the shape of a leaf or the bend in a river, is the observation. Has that nothing to do with who made that. It is all about the observer getting the idea that that observation is useful, so that the observer, with the observation, and with the artifact that comes from doing something, acting, based on that observation, the observer becomes a more empowered mover of itself or herself, himself on the landscape. So that's design. And so design is one of the most universal phenomena, the most universal phenomenon of value to us that exists. It's right there or down there with gravity and with irreversibility, the second law of thermodynamics. That's
I agree
design.
with that entirely, but isn't that a lot because of it's just constraint? That there's physical
Quite the
constraints.
opposite. It's about freedom, not constraints. Without freedom, on the contrary, without freedom, there is no discernible image, no change in that image, no evolution. And
But you can speak to this better than anyone because it's like that. It's certainly, I mean, that there is constraint within the physical world and stuff of that. What organisms are capable of doing and not capable of doing.
Sure. I mean, the classic example of this is the laryngeal nerve in the giraffe, right? Which this is a sort of a case study in evolutionary biology. The laryngeal nerve in the giraffe branches off the vagus nerve in the brain, travels all the way down through some arteries in the heart, and then back up the neck of the giraffe where it innervates the larynx. Why would it travel all that way down and all the way back? Well, it's just because of the constraint from its ancestors. So that design, if you could call it that, evolved in our fish ancestors, and that constraint, that physiological constraint, remains in the giraffe, even though it causes this bizarre sort of morphology. But I think when you're speaking about freedom that comes as part of design, as an evolutionary genomicist, I think of that as variation, the raw variation that is necessary for adaptation. Right? And I think one of the interesting aspects to consider when we think about nature and whether it's as the Da Vinci quote that we were provided with suggests, that nothing is extra in nature because it's so finely designed for its environs. If we look at the genome, say the human genome, 3 billion base pairs, 50% of that, fully 50% of that is repetitive DNA with no known purpose. So, there's a lot of extra stuff out there in nature, and surely it's shaped by constraint, but it's that variation that allows freedom to adapt.
I could respond to that, but you haven't spoken, so.
I'm just biding my time. Well, maybe just so I'm trying to understand when you talk about freedom. So I guess, I come out of physics, and so to me, all that we're talking about here, and what you've talked about is, boils down to, well, the constraints. There are constraints of, I don't want to use the word design. Wow, that's terrible. I don't want to use the word design. Everything is finding its way through a complex energy landscape. I mean, as a physicist, we always resort to this. We always say, well, it's all about finding free energy to do work. So our molecules are doing that all the time. Our DNA is doing all that all the time. It's the root of biological evolution at some level, is these organisms, they're exploring this vast chemical landscape, and where there is opportunity to extract free energy and do work, it will happen. And why is that? Because the whole universe is driven towards dissipation of energy, right? And moving towards a higher entropy state. And so I guess is that the freedom that you see, is that this vast energy landscape that everything from the river to the molecule is exploring?
I will Okay, since you, I like that you speak the language of thermodynamics. I'll try to make it more readable to everybody. First of all, I like the title of your blog, Life Unbounded. Here's a comment on the so-called constraint. It does not exist, okay? There's the space is to be accessed by these flows that you bring up, the flows that are driven by the power that you bring up. The so-called free energy, a much better name for that is fuel or food for those of us who live on this planet, is converted into the power by engines, and most of the engines are natural. Okay, animals are basically engines on trucks. And of course, we are now very lucky to be riding on engines made by smarter humans 200 years ago in Britain, and propelling us much more cheaply. But the question that is not being addressed until now is what is that power coming from the free energy useful for? To what end? And the end is for greater, easier movement into this free space, and yes, available time, because obviously, here I speak autobiographically, I like to live longer, and so I could move more easily all over and bring others along with me, you see. So that's the tendency. As Niels Bohr said, nature is about us. It's what we say about nature. That's what's interesting. So that's the beginning of a more inclusive picture of the topic.
I read parts of your book, and I had a question for you. The constructural laws that things tend... Constructive.
If you can say fractal,
okay,
then
it's constructal.
Constructal
law is that systems move towards more easier and easier flow.
Easier, greater access. I like to, yeah.
So I mean, just a couple really everyday examples. You know, my drain gets plugged up. It seems like it's went from less easy flow, for easy flow to less easy flow, or arteries get clogged. So how do you deal with examples like that?
Those examples are very different. Your drain gets plugged up because your drain, the pipe is not natural. It is not it's not free to morph, to live with the incidental blockage. The pipe is your artifact. The drain is you, the human and machine specimen. The river basin is the natural counterpart of your example. In the river basin, I grew up on the Danube, and I've been observing as a kid going fishing. The river basin gets the tree log out of the way. Tree logs do block the flow, as does the sunken ship. Right. But the river, because it is free to morph, because it is alive as a flow architecture, as a sign, as a thing that impresses you, has the natural, the intrinsic property of evolving to flow more easily.
So what about arteries? Like
arteries?
Yeah, like people.
Same thing. The artery also does its best until it's old enough to split, to basically cause an aneurysm, to do all sorts of...
But it seems to have gone from, when you're younger, your arteries there's more free flow. So the evolution there seems to be from more free flow to less, and that's what...
No, the life of a human being is not evolution. It's called growth. Many people in science confuse the life of the individual with the evolution of the species. No, evolution is about
I'm not sure we confuse it.
Huh?
That's what we think is right. It's part and parcel. A single organism is one instance out of a vast evolutionary landscape, right? And it's playing. So I hear. Are you suggesting that there's agency in a river or in our arteries? I mean, that's the sort of, I hear that in the language, but I'm not sure that's what you're suggesting.
Okay, what is your definition of agency? I mean, literally, the dictionary definition of agency.
Well, no, I'm asking you. Are you
No,
saying?
but you use the word. You use the word.
Well, is the river somehow deciding?
No, agency doesn't mean that. Agency is essentially power. Power, which is that makes action possible. Agency is not about the direction in which the design change happens because of the power that is used. The direction of the change in flow architecture, because of that power, you brought up the engines earlier, that is actually the phenomenon of evolution, which is of all physics, and which is summarized by the constructor law of physics, which is really the statement that everything that is finite size, not quark or infinitesimal or invisible, finite size, including the celestial bodies, has the in order to persist, which is that means to live in physics, it must evolve freely toward greater access, or in your example of the universe, toward the faster route to equilibrium, which means death.
But why then, in a biological or an evolutionary context then, I mean, that if you take it back to looking how evolution works, why are there then unoccupied ecological spaces? Because is that if you, I mean, we just did with my students, we just did something for an exhibit that we want to do, and you can look at like a three-axis graph of a three-axis projection of bird eggs, for instance, and you can, like, one axis is size, one axis is shape, and then the other axis is color. Okay.
The third is what?
Color.
Color.
Yeah, and if you would look at it if you'd say, yeah, you know, that evolution is a great optimizing thing, you would expect that the whole kind of thing would be filled in universally, but it's not. There's big empty spaces in a lot of it,
right,
of where are just unoccupied ecological spaces. And I mean, that's just one example. I mean, people have recognized that for a long time, and then once in a while some major evolutionary event happens. I mean, previous to about 325 million years ago, there was nothing that weighed over 25, 30 grams that flew. And then all of a sudden is that flying reptiles, pterosaurs evolved, and then also birds evolved then, you know, later on.
Yeah.
And then all of a sudden that was unoccupied ecological space that became filled in. And because of, you know, whatever happened, but nevertheless is that it's very, you know, it just doesn't go with this kind of thing, that there's always just this undercurrent of...
I can respond to you by speaking a language that most people know, which is that of looking at the river basin morphology, the map. The wetland, the rain keeps falling, is wide open, but the river channels, all hierarchical, happen only in some places. There is lots of space that's not invaded by, meaning design, you call it design space, or for that matter, energy landscape. There are lots of, most of it is actually not bathed. And the reason is that in order to bathe with flow an area or a volume, the easiest, meaning the greatest access to the entire space is offered by a vasculature. This is why all these things that come up are happening. You mentioned repetitive DNA in this theoretical infinite space of DNA combinations. The reason is that all DNA is not equal, just like the words in a language. Most of us speak basically a hierarchy of words, all of them very few. It's called, it's much smaller the number than the main vocabulary, because that is the way to speak easiest and the way to communicate with everybody else the fastest. So you talk about these things that look the same, that have two eyes. Well, they had no eyes before the Cambrian explosion. But then,
but they're still limited by like their singular history. Is it all life descended from a common ancestor? So we're stuck with that.
let me just say one more thing, which is the punchline. So when the eye occurred, obviously 2 eyes were better because the world is flat. These beings were perceiving the ambient, which is flat. Okay, the 2 eyes oriented this way, not this way. And that's right. And as soon as that happened, movement became immensely easier, safer, farther. Just like after the invention of radar in military aviation. And so that's why you talked about the nature optimizing things. That's why this trait stayed. The traits that are in fact inferior to existing alternatives do not stay. What works is kept. That's evolution, and it's a random up to a point. In fact,
that's kind of a weird view.
Yeah, I find it hard to. I mean, and that example of why I mean, there was bilateral symmetry in organisms, I think, before complex eyes evolved. So I mean, there are whole other reasons for that. I'm not an expert in evolution, but.
Well, I mean,
Yeah, and in terms of the repetitive DNA, talking about the reason that exists in the genome. Certainly, not all organisms have the degree of repetitive DNA that mammals have, but it's thought that that's the result of viral elements, viral DNA that that actually come and insert genomic elements that will copy DNA over and over, and that's what they do for a living. So a viral infection into your genome can result in many of those events. So, I think most people consider that to be a random process.
yeah, I mean, like birds, for instance, have tiny genomes compared to mammals, and
Yes.
their ancestors, crocodiles, have genomes which are not ancestors, but the closest living group to them, have genomes which are far larger than birds are.
look, there is the river basin that has no genome, yet it looks just like the human lung. Okay, so
Yeah, but that's not
correct.
that has nothing to do with it, because it's like that it doesn't have a singular history. It's not related to every other river basin in the planet.
And I think that's an example of, people who study complex systems are always talking, I mean, I'm sure you know this, that talk about scaling laws, for example, that exist across all sorts of things. So there are scaling laws in biology between body mass and metabolism, right? And it's across all organisms. And it's a result of some approximate optimization process, but it's still playing out over billions of years of evolution. It's the same scaling law that exists in language, right? It's a thing called the zip law, right? It's the word use frequency versus, these are all, I think, as a physicist, I would say that a lot of what you're talking about, the rivers and so on, yes, there are similarities to biological systems, but they're for slightly different reasons. They're not because of inherited traits, right? They're because of, and this perhaps gets back to the universal idea of design, that there are these emergent scaling laws, these emergent relationships because of the underlying nature of systems driven by, finding their way through some energy landscape of optimization, of efficiency, and so on, right? I mean, I think these scaling laws also apply to our circulatory system.
Right. And things like the species area curve, how many species you find in 1 square meter versus 100 square meters.
Let me try to clarify the words we speak. These scaling laws that you mentioned are not laws of physics. They are compact mathematical summaries, also known as correlations of observations. Mm-hmm. The law of physics is the purely mental viewing that empowers one to predict such correlations. And that is what I do. And along the way, what I predict is not only the correlations and all these things you bring up, including ZIF. I predict why, at what point the so-called correlation should break down. Because yes, there is a scaling law to the many ramifications in the human lung, but with a constructed law, I predict that the cutoff should be 23 branching levels. That is the power of a law of physics. So yes, most of my colleagues use the word law when in fact they're talking about an empirical activity, which is that of making it more compact, a huge volume of observations. The law of physics does that one better. It makes even more compact a huge number of these correlations.
I'm just going to go back to something previous. You said you disagreed about the fine-tuning, so I want to hear
Fine-tuning, yes.
Yeah, your take on it, and then...
Well, I mean, maybe would it be useful if you explain, do you want to explain a little bit what fine-tuning is, and then I can...
Okay, so what's been discussed pretty much since the 70s has been what's called anthropic fine-tuning, and that the universe is in many ways the fundamental structure, precisely set so that life can exist at least somewhere in the universe. Okay, and I usually like to refer to the kind of life as what I call embodied conscious agents, which would be a generalized version of what we are. And so you could do this on different levels. There's the laws of nature, the very general principles, like the law of gravity, or that unlike charges repel each other. And there has to be the right set of those. If you pulled off the law of gravity, there weren't any law of gravity, there wouldn't be any masses wouldn't clump together, and obviously you wouldn't get highly complex beings like us. There wouldn't also be stars, which are the energy sources for them. And then the most discussed area of this is on what they call the fundamental parameters of physics. So those would be like the mass of the proton, or even more fundamental than that is the mass of the up and down quarks, which compose the proton. Other examples would be the strength of gravity as not just the strength on any given planet, but that constant G in Newton's law, that F equals G, the mass, first mass times the second mass divided by the distance between them squared. There's a number for that, and you can express that. For those who've had physics training, you can express that in what's called dimensionless units. You don't actually have to refer to units there. But anyhow, it's a number that gives the strength of gravity. There's a number that gives the strength of the electromagnetic force, the strong nuclear force, etc. And those have to be precisely adjusted over vast ranges of possibilities in order to have a universe that allows for what I would say would be life, more generally stable, reproducible complexity. And I can give more examptions than those, but there's lots of examples you can give. But that's the general idea.
Right, and I think what is so, and I'll get to why I sort of made my squeak about objecting.
Okay.
What's so interesting about that is, as part of this topic of design and nature, is that it could be construed to mean that everything was set up, as you say, to be just so in order to enable the production of things like stars in the cosmos, which in turn produce heavy elements in just the right abundances to ultimately make planets with chemical compositions that allow for the sort of complexity that life can emerge from. And and I've been interested in that for a while, and what's so interesting to me actually is that now we come back and look at it with a little more scrutiny, and I'll explain this as well, that that fine-tuning is probably not so fine at all, which negates some of this idea that the universe is perfect for life, or just appears to be perfect for that one instance of cognizant life that you talk about. So I have two things to say, and one is to do with people's investigations of that quite recently that seem to suggest the universe is not fine-tuned particularly well. The other piece of it is, I think you can flip it around and it's predicated on the notion of life being a very particular thing, right? Carbon-based organisms, somewhat like us. And the truth is, we don't know whether you can build life out of other building blocks or not. Suppose you can. Suppose life can be more general as a phenomena. It can be can come together out of any set of building blocks that allow for sufficient complexity, right? And maybe that's, I mean, everybody always says silicon, but silicon probably isn't a very good element to be involved in this, but it could be. Then that could conceivably change the perception of the universe being particularly well fine-tuned. But I just wanted to say, and this is why I sort of, got excited when you mentioned it, that, so there has been recent work on this from the physics end. You may well be aware of it, that, for example, you mentioned the relative strength or the strength of gravity.
Right.
Right. And so one of those dimensionless quantities is the strength of gravity to the strength of electromagnetic forces. Mm-hmm. That ratio has been deemed in the past as something that if that was changed just a little bit, you couldn't make things like stars, right? Because a star is essentially a competition between gravity and electromagnetic forces. It's in a sort of dynamic equilibrium as matter comes together. And so the argument has been, well, if you changed gravity a little bit or you changed electromagnetism a tiny bit, you just wouldn't make stars and all that then follows. But recent investigation of that suggests that, in fact, you could still make stars even if you changed the strength of electromagnetism by maybe a factor of 1,000. And if you change the strength of gravity, the G constant, by up to 1 million, or maybe even 10 million, that space, that parameter space, still allows for stars to form in the universe. Now, they might be different than the stars we're used to. They might be much bigger, but they would still go through the same cycle of nuclear fusion and element production. And to me, that's really interesting, if that's true, because it means that at least one piece of the fine-tuning argument, and I know there are other factors to that, other fundamental properties that if you tweak them a little bit would be seemingly problematic, but that suggests to me that it's first of all, maybe the universe isn't particularly well tuned for life as we know it. I mean, we don't actually know, because we've only got the one instance that we know about right here on the Earth. So we don't know whether this is a fertile universe or not a fertile universe. And that, to me, would change, suppose 500 years ago or 400 years ago, first telescopes, we just saw life everywhere. Everybody had big neon signs out across the universe saying, "We are here. What are you up to?" "Oh, yeah, Renaissance, lovely." We had that, 1,000 years earlier. Then we'd have lived with a universe replete with living organisms, and I'm not even sure the question would come up that the universe was fine-tuned.
If what? I didn't quite catch your last scenario.
Suppose the universe, we had known that the universe was packed with life.
Okay.
There were planets everywhere, and all of them had life, and it was all sophisticated, technological, it had evolved in many different ways, and so on. I just wonder whether we'd even ask the question. And the thing is, we don't know how fertile the universe is. So sorry, I'm loading this with lots of...
One thing I want to say, okay, we'll start with the response to your second point you made about assuming carbon-based life. Most of the arguments actually don't. For example, the fine-tuning of the cosmological constant, which governs the expansion rate of space, that's simply, if it wasn't within a very small range, typically estimated as 1 part in 10 to the 120th power, very, very small number, that the universe would expand too rapidly for galaxies and stars to form, so there just wouldn't be planets, there wouldn't be stars, and then you're not even going to get any kind of complexity. Or if you looked at the level of laws, if you didn't have like the strong nuclear force was long-range force, wasn't just right, you wouldn't have atoms. And concerning your case, so first of all, I'd say the more general, if somebody's correctly formulating this, most cases are not simply focused on carbon-based life. There was that case with Fred Hoyle initially with the carbon and oxygen, but most of them aren't. And the second thing, in the example you mentioned of the star, I don't think that it's just whether stars could exist or not was dealt with the gravitational constant, defined structure constant. It wasn't just a matter of whether stars could exist, but whether they would have the right temperature, last long enough for life to exist. And there's also, if you change those, there's planetary effects, like the ability to retain an atmosphere. If you increase the strength of gravity, fairly easy to show that you're forced into increasing the surface force on a planet to retain an atmosphere. And so, gravity is very weak as a force. It's if you did it in dimensionless units, about 1 in 10 to the 38th power of the strong nuclear force. And if you increase gravity by, let's say, 1,000-fold, then only planets will have 30 times the surface force strength of experience. It would be a lot less, I think, ideal for our kind of life.
So
I think the argument actually can, when you start talking about the conditions being even optimal, you might even be able to get life, but it's going to be, as you increase the surface force, it's going to be a lot harder to do much of anything.
So I would agree that figuring out all these secondary ramifications is tough, right? And it may be that you would eliminate regions of this expanded parameter space. But no, I mean, the example I gave, that range, and I'm sorry, this is getting into sort of horribly specific sort of physics, so we should veer off from this again. That range I gave for strength of gravity, strength of electromagnetism, is the range from which you would derive sufficiently long-lived stars with the right sort of properties to produce, as far as we can tell. I mean, you'd have to run a lot of nuclear physics simulations. An abundance of heavier elements not so dissimilar to what we have at the moment. No, I mean, I raised it not really just to sort of attack this idea, but it's interesting to me that, and maybe this almost relates to what you were saying. I mean, we impose design on things, right? That's us. The universe may have nothing to do with that. Right, we tend to impose design more than anything else.
Would be you just look at the range of physically possible values, and then you look at those values that allow for complexity, and some of them are much more straightforward. You don't have to run the kind of simulations, which would be like the cosmological constant.
Yeah, I mean, I think the cosmological constant is a good one.
It's much more straightforward.
Yeah, right.
And then other ones, and the planetary effects of changing gravity are pretty straightforward.
But if we bring it back to this idea, just how messy all this stuff is, basically. I mean, the best example of that is, I mean, even if you bought into the creator kind of stuff, that Adam and Eve, everything, I mean, just look around. We all look different. We wouldn't, because DNA replication is incredibly messy. And that there's, all of these things, whether it's, talking about things within the aspect of the beginning of the universe, to things that E. coli mutating in petri dishes around the city in different labs. I mean, that there's a lot of messiness and a lot of stochastic kind of things that just happen to all of these things.
And if it weren't messy, we wouldn't be here.
Exactly.
Well, let me contribute.
I think she was.
No, I was just going to add to that. And we, as I think you're saying, are predisposed to see the design and everything, even if it's created by random processes with additional constraints on top. And that's part of not just our brains, but animal brains in general that are designed to look for pattern. That itself is adaptive.
Because the brain or any other such organ is finite size and it can only do this little in order to enable the moving vehicle. I've been listening to your discussion.
That we don't use a lot of our brain.
Well,
so if you say it's too small, well, why don't we use more of it?
No, the point I'm making is that from one generation to the next, we're exposed to more information, more observations, reams and reams of this. And of course, we absorb it in the forms of principles and correlations, but not number by number in the immense volumes of tables of data. We become more knowledgeable through hierarchical compression, not through mindless accumulation of volume. That was the point I was making. I want to contribute to this discussion because several points were made here. First of all, I was learning from the exchange between the two of you, which is basically about physics. The topic today is design in nature, which is something that is familiar to everyone. It's something for us mortals here, somewhere halfway between the stars and the protons and the quarks. Now, many people, as you implied, equate the quark, the proton, and the infinitesimal with, quote, even more fundamental. Smaller does not mean more fundamental. Fundamental, fundus, in Latin means at bottom. Look at the Statue of Liberty. The pedestal is bigger than the statue. The thing, or the fired brick in Roman architecture is finite size. You can kill a man with it. And it is fundamental because before that, the buildings were really, really miserable and crumbling. Earthquakes and so forth destroyed most of them, but not after the fired brick. You have these vaults. You have architecture of a different kind. After the fired brick came the steel reinforced concrete all over this country, skyscrapers and iron bridges. Okay, so that's fundamental. A finite size elemental construct. This thing, the brick, the steel in the cement. These are fundamental because they are literally at the bottom of lots of things, not if everything. So in science, unfortunately, language basically has a life of its own. Some words are so useful that they end up being used, actually misused, in other places. The life carbon-based. Of course, that's the view if you equate the design in nature only with animals, with the biosphere, you see. But design in nature is general. It's not about that. And so there's a famous question, what is life? And I think the answer is very easy if you know thermodynamics. Because in thermodynamics, this is the part of physics that had to be born after the steam engine, the heat engine 200 years ago. Thermodynamics, actually Maxwell in Cambridge, one of the key concepts in physics is that of the dead state. Death is resolved as an answer to a question in physics. Dead means in a system, which means this that you're discussing, that system is in the dead state if in it nothing moves. That also means nothing morphs, nothing changes. Well, the antonym of that is the live state of a system. It is a system in a state occupied by flow, meaning movement, and change in configuration. I mentioned earlier, change cannot happen without freedom to change. That's another basic concept in physics. Process means change of state from this being of, say, the pot of water to this other being of the pot of water. So all these things together, taking us from what everybody understands and accepts, which is dead state in physics, life state, the antonym of the first, and then change in state, which happens because of freedom. That change is evolution. And the direction of that change is not the haphazard. It is in one direction, which is that of, changes that facilitate the occurrence of configurations that offer greater access, or all the way to more efficiency, to smarter economics, to faster speech, or cheaper communicating between entities that want to communicate, or the fact that it's called economies of scale, the fact that it's easier to move as a group, not as individuals. And on and on and on. This is the river water, the two people entering the stadium. This is physics. It's everything showing the same tendency to morph and to surprise the observer with, surprisingly, the same kind of pattern. Pattern is not design. Design is a flow configuration with freedom, but also with a message.
I get the impression the way you talk is that all of these questions that are being raised and all of the debates that are happening, that you seem to present it as if you already have all the answers. And I'm a little bit puzzled by that because obviously these are unsettled issues.
Well, look, since you put it that way, I have to respond right away. That goes without saying. Okay? No. On the contrary, I'm the ignorant who came to this very old and big table of discussion. I'm talking about in physics, in biology. I'm from engineering. I'm a person who basically was not supposed to be here. But it so happens.
You are here.
No, I'm talking about it is only now that I publish, meaning 20 years ago, I published in physics and biology. Previously, I was preaching to the choir. My peers in engineering get it. They are simply not invited to discussions on design, even though the word meaning design is what people do. Incidentally, this thing with signum in Latin, then it became disegno in Italian. The West got the science that we cherish today from the Renaissance. That's how we really got it. And then through the French, dessin. So it means the sign. It doesn't mean the act of designing something and making it. That's something totally different. Design happens. But to finish your point, when I started to talk about the physics of evolution in this most general sense, not as chemistry of carbon, okay? In the most general sense, I was surprised to hear from my peers, those who came to the constructor law from physics and biology, that what I'm telling them from my direction is in fact not only familiar to them, but it covers what the contemporary scientists regard as known in their various compartments, like departments on a campus that do not talk to each other. So that's the reason.
I think it questions it.
Well, I want to go back to a previous comment, and that was a comment you made about that the brain is programmed to see design in nature. Now, one could take that as the brain is programmed to mislead us because there's not near as much design in nature as the brain seems to want to think. And in certain areas, that's certainly true. But I would want to point out that from the time of the scientific revolution, I could cite Morris Klein on this, who said the assumption everybody was making was that nature, since the time of the Pythagoreans, that nature was mathematically designed, meaning in particular mathematically put together to realize elegance mathematics. Sure. And that, during the last century, ever since then, has been just enormously fruitful. You have people like Paul Dirac, one of the major founders of quantum mechanics, says, the equation must be beautiful. It's more important than an even match experiment, because sometimes when they pursued beauty in the equations and they seemed to conflict with the experiment, later it turned out to be correct. That was Einstein's approach. It was, he would actually, as major biographer said, he would think of, even though he didn't believe in a theistic God, he would think to himself, if I were God, what would I do? In other words, how would be the most beautiful mathematics to put this together? And that was a guide for him, and has been a continual guide and a very successful one. So I wouldn't want to make the inference that our brain being, I think we have to resist the inference that means it's going to mislead us. It's actually amazing that that kind of idea has been so successful at an area we wouldn't expect it, because if it was programmed for reproductive success to see design and everything, and to see these elegant patterns, we wouldn't initially expect it to work at the underlying level when the mathematics is far removed
I thought you
from
were
what we
saying it may
see
not be as beautiful
on the
as we
everyday
assume.
level.
Did I misunderstand you? That some of the mathematical beauty may not be as...
Well, no, I mean, I think there's enormous beauty in this context for mathematics, and I think it's a very interesting point that you raise. And as you were talking, I was thinking about this and thinking, okay, so why do we do this? Why do our brains do this? Is it because, again, we've evolved, presumably like other species, and so that our brains are part of a data processing system, right? And we're bombarded by millions of pieces of information all the time for every nerve ending, everything we see, everything we hear, smell, pheromones that are floating around in this room that trigger all sorts of things. And it's a lot to handle, right? But, there's a tiger waiting to eat me over there, so I'd better make some good judgment decisions. And this is a very naive way of thinking about it, I suspect, but does that seem like a plausible reason why we see patterns, we see beauty in certain equations? There was some report very recently talking about the study of people doing math, and I think even looking at fMRI scans, why they were solving mathematical puzzles and getting that pleasure. I don't know if it was dopamine or whatever. Does that make sense? Yeah,
I'll just mention as a quick example from fish. Obviously, where our brains are more complex, and understanding our predispositions is more complicated. But there's a very lovely long-term study of guppies in Trinidad. And these guppies, I'm sure a lot of you have had guppies as pets. They have these beautiful tails, very colorful. And the tails are, the males have the colorful tails, and it's thought that these are to attract females. The females choose the males based on the color of the tails, which are kind of this bright orange color in this particular area. And so for a long time, the research was completely focused on why the females prefer these beautiful, colorful tails. It's lovely, they look designed, right? And then some smart team came along and thought to examine what the guppies were eating, and it turned out that these guppies prefer these orange berries that fall into the river that have a very similar color and pattern to the male's tails. So it turned out the females, at some neurological level, had a preference for orange, for this bright orange color of the male's tails. And that, on an evolutionary timescale, got translated into a preference for males with these bright orange tails. So something that looks completely, unrelated.
How
turns
does
out
that apply to humans?
Yes, good question. So
I am curious.
well, maybe somebody with
So how does that connect up with our brains being programmed to see elegance and beauty?
Just that there may be, at an evolutionary timescale, some predisposition due to selective forces that we don't see around us anymore, but that it may have been part of our evolutionary history.
But it still would be the case that why would we expect that to work when in areas that are so far removed from what helps us, in our long evolutionary past, survive, namely at this fundamental mathematical level, which is actually very abstract. That's why people have a lot of difficulty learning quantum mechanics or general relativity, because the mathematics is far different from it's a difficulty explaining how we can even do mathematics in the normal, from an evolutionary perspective. People have worked on that. But that's the ordinary counting, fractions. This sort of mathematics is very far removed, and as Eugene Wigner wrote a famous essay on this, as he pointed out, the mathematics is chosen for its elegance and fruitfulness mathematically in being able to, let's say, solve equations. And so why would it work so well there? That's the puzzle I'm pointing to.
But I guess, quantum mechanics, right? To do quantum mechanics, you have to know stuff. Mathematics as we have it. And so I'm just, it now looks, we see quantum mechanics mathematics, but that beauty wasn't arrived at like that.
No, it wasn't,
right?
but the mathematics using that mathematics into complex numbers was developed before the arrival of quantum mechanics, and it's essential, either that or something isomorphic to it is essential for quantum mechanics, and that was developed because it was enormously fruitful, and complex numbers are a real number plus an imaginary number, which you can think of as the square root of -1. And so they were developed because it was enormously, one reason you can solve like third order or more, or any polynomial using the imaginary numbers, but you can't using the real numbers. There's no, and so they were enormously fruitful algebraically and in other ways. And it was developed all independently, yet this, for aesthetic reasons because of its mathematical fruitfulness, and yet that's just the system that nature is, the mathematics that suits nature.
I wanted to just, you didn't finish your point about the fish.
No, it was pretty much finished.
Yeah, so
yeah, I'm hoping that somebody that knows a little bit more about the human brain could, take it a bit further.
The conclusion being that in terms of what was making the female fish choose that was was not really a design, was more something else.
Right. There was a predisposition that looked to us to be sort of design related at first glance, but turned out to have a deeper evolutionary history that shaped this preference based on food. Yeah.
All right. So the ability, maybe the thrill of adding two numbers together is related somewhere in our deep evolutionary history to the ability to think, oh, if I go over there, I get two berries instead of one berry, right?
Well, I mean, I think that, one of our colleagues at Columbia and stuff, Eric Kandel and stuff, is like that, he's made his career, won his Nobel Prize just on the basis of how that every single interaction you ever have, everything you ever look at, not just changes your brain chemically, it changes it physically, is that new synapses become, larger and hotter, and that, that there's been a huge amount, basically we know about the brains of three things. We know some about human, we know some about mouse, we know a little bit about C. elegans, if you want to say they have a brain or not, and then a little bit about zebrafish. But certainly, they've been able to demonstrate that in some experimental organisms as well. So like that, we can talk about this set of complex mathematics, but these are relatively new things that are basically, things that have come since Newton's time. And that, so our brains, when we look at mathematics today, look fundamentally different than somebody who would have thought about those same sorts of problems before those mathematics were different. And not just in a chemical way of just studying and understanding it, but in a physical way as well.
I want to bring the discussion back to design and nature. And respond to two things you brought up, or actually both of you. Why is the brain programmed in you as well to detect pattern? You see that, by the way, right now in the famous story about the NSA using big data in order to discern patterns that are useful, and that's the answer to your second point about beauty. Why is the pattern useful to the NSA? So that the government could act faster in the direction of protecting all of us. The same with the animal. Obviously, 1 million years after another million, learning that what is good for it is actually pleasure, because to live is the option that we all like, as opposed to becoming the victim. And so beauty in physics is a part of this evolutionary design, meaning changes that we make every day in how we move in order to get going, to go through life easier. We like a simpler equation because we get it and we move on. My best example is why statistically it's been proven that most people like to look at the images shaped like this. Like the business card, or like the computer screen, or like the screen of the cinema. This shape happens to have a length to height ratio approximately the same as the golden ratio. That's a coincidence. But why do people like this shape? Why? Because this is the area that's the easiest, the fastest to scan with 2 eyes. Okay? This is the animal in the business of surviving and getting out of the way of the predator and looking at the world, which is flat. This is why the animal has 2 eyes on the horizontal. And by the way, the area, the ocular area of the 2 eyes is an area approximated by this shape. And that is then the beauty, which goes hand in hand with locomotion and with greater access and with survival. So you have intangibles like beauty, as of course all the way to economics, that actually belong in physics.
Oh, I'm sorry, go ahead.
I was just wondering, can anybody comment on the evolutionary biologist on Simon Conway Morris's thesis? I'm just wondering because that's, I think, very relevant to the discussion here of that. That the built-in constraints already there from physics, chemistry, etc., make almost inevitable certain kinds of organisms. So he's bucking the idea, particularly popularized by Stephen Jay Gould, that if you ran the evolutionary tape over again, you'd get very, very different types of life forms, and that it would be a miracle to get a miracle in the sense of being very, very improbable occurrence to get beings like us with our level of intelligence. But he thinks that the evidence of convergence, things like the compound eye occurring independently many different times in evolutionary history, indicate that these sorts of things are much more inevitable than we once thought. So there is a sort of inevitable set of patterns that are going to occur in nature, despite a lot of the accidental character of mutations. And I'm wondering what you think of that thesis and any comments you have on it.
I would certainly agree with Simon on that one, because I think that the evidence of convergence is so great that we can see that the same kinds of teeth occurring in different kinds of vertebrates who eat similar kinds of things that are totally unrelated from one another. We see that the same kinds of, what I was alluding to before, of these empty ecological spaces that are occurring in lots of different groups, be they insects, be they bats, be they birds, which that occur over and over and over again. That there's something which is just some physical constraint which is keeping it, out of that. So like that, that we see things like that, the sizes and shapes of eggs, something that that our lab has studied, and things that you see that different groups which have lots of different sizes, lots of different kinds of things, that they come up with the same shapes all the time. So like that they don't go way out of bounds. So it's really I think that if you ran the evolutionary tape over again, we might not be mammals, we might not be related to things. Maybe we wouldn't exist, but the kinds of biodiversity you see on the planet would be partitioned pretty much the same way. Just like what was partitioned with totally different animals during the Paleozoic period 200 million years ago. And then when the big extinction at the end of the Paleozoic, it came back during the Cretaceous period with the same kinds of reefs, and then it came back again in the Cenozoic as well with the same kinds of reefs. The animals to a non-biologist would look pretty much the same, but they're totally unrelated to one another. So,
to that I contribute the addendum that it's this thing that you're describing is actually predictable, and it's not only about the population of these beings, but actually the movement of these beings. The locomotion is in fact the physics. The shape of the egg is physics, it's predictable. The frequency of the egg laying is physics and is predictable. And yes, the configuration of animal mass movement on the globe is no different than the vascular configuration of the movement of all the other water, which is much older, which is the water in the river basin, or the movement of air currents on the surface of the globe. It's hierarchical and with design. I did some reading about my colleagues here, and I developed questions. And one is to you, if you'd like to address it, because time is running short. Would you comment on two things? One, I hear my colleagues in academia wringing their hands about the conflict between science and religion. That's one. And second, about your own interest and specialty in a theory of atonement.
Okay. Oh, well, I think the theory of atonement is going to be somewhat off topic, but if you want me to comment on it, I can. But in terms of is there a conflict between science and religion, I would say no. I think science and religion, at a deeper level, there's these superficial conflicts. For example, young Earth creationists with their literal interpretation of Genesis is in conflict with what we know from science, that human beings, apes, and other creatures are genetically related. So there's the common ancestry thesis. But at a deeper level, I think the kind of, let's say, the belief in God in particular, and if you want to go more particularly Christian, the belief in the logos, the reason, that the world is an intelligible whole and ordered in an intelligible way is deeply consonant with science. In fact, most of the people, in fact, all the people who began the scientific revolution believed that and thought that. Galileo thought that the universe was written in the language of mathematics, and likewise Kepler. But what you have to be careful of is what level you're looking for this, in what level you attribute to chance and what level you attribute to a more fundamental kind of design. For example, Kepler, he spent the early years trying to figure out a mathematical order to the actual distance the planets were away from the sun. So we looked for the 5 Platonic solids. And that never worked out because the distance the planets are, that's a matter of chance, not necessity. But their actual elliptical orbits and the speed in which they go, that's a matter of physical necessity. So he finally eventually found Kepler's 3 laws of motion, which led to Newton at that point. So I would say, no, there's no, in fact, at a deep level, they're consonant. There's only this superficial conflict.
David?
I'm sorry?
What would you say about?
That sounds good to me.
So I don't think the conflict, but I mean, what we get from the popular image is this conflict. And it was also a thesis promoted by, which historian friends of mine say, and people who are in the history of the science and religion, whether or not they're believers or in God or not, like Anderson Dixon White, I think he's the first president of Cornell University, promoted this perpetual conflict thesis, and the history was really, really bad history. The footnotes didn't go anywhere, and so that, from the historian's perspective, it's way more complex than that. There's been skirmishes, but there's also been a lot of support for science from the religious community. So that would be my main.
Well, I would agree with all of this history, absolutely. I mean, someone like Kepler was deeply religious, that's my understanding. But he also felt that that was perfectly compatible with this empirically studied quantitative universe. But I mean, he was even capable of taking quite risky steps, because my understanding is, before Kepler, people assumed that the movement of planets was all in perfect circles.
Right.
And Kepler took this leap to say, well, maybe they're ellipses, which is pretty shocking for someone who...
Well, it was motivated by there's an idea, the underlying idea of elegance, that heavens were elegantly ordered, would give you the perfect circles, the most symmetrical. But he was willing to break that. But it was still that underlying idea of an elegant order to the universe. It's just you can't get too fixated on a certain version of that. I mean, Einstein got fixated on a certain version of that and never could really accept quantum mechanics. So, and sometimes a religious motivation can be very helpful. I mean, the developer, Lemaitre, who developed the Big Bang Theory, was religious, and it was people like Fred Hoyle who opposed it strongly until the evidence came in the 1960s. Even then he opposed it. I think he never did accept it. He couldn't imagine the universe having a beginning, but somebody from a kind of theistic perspective, that was much easier to imagine. Einstein couldn't imagine the universe having a beginning, and that's why he introduced originally the cosmological constant to get an eternal universe. So in that particular case, you can see that actually the religious belief actually helped the acceptability of the Big Bang theory.
So you are saying that on a surface level, religion and science may seem not compatible, but on a deeper level, they're compatible.
Right.
How are they compatible?
The idea of theism, that's what I was saying, the idea that there's a God who created the universe and the intelligence behind it would lead you to expect that there'd be, the structure of the universe would be intelligible. It would lead you to expect it would be elegantly structured at a fundamental level. So, and that we could understand it, and that's been a mainstay of science, is that we could actually understand the universe, which wasn't given to us, that most cultures didn't assume we could really understand the underlying nature of things.
But how would you, how would you ever, like, as a scientist, you work in two domains. You work in mathematics, where you work with mathematical proofs. Then you work within the construct of an observationalist, which you test hypotheses. How is the idea of God a testable hypothesis? How would you test that?
Well, the thing is, you're demanding that what you're assuming is all knowledge is scientific knowledge, and all the hypotheses you have about the world can be gained by science. A simple refutation of that is your own consciousness. You'll never get to your own consciousness by a scientific study. You know you're conscious because you're aware.
I'm not sure I know my consciousness.
Well, assuming you're conscious, okay. So, or moral, if you hold to moral truths, you're not getting them by means of scientific investigation. So I wouldn't subscribe to God as a scientific hypothesis. I think that's a big mistake to do that. So you can't test God, test the God hypothesis.
So isn't that a slippery slope when it comes on to other things then, and saying, well, this isn't really scientific, it's just...
Well, there could be evidence for things without being scientific evidence. I think you have evidence in mathematics, which is not strictly speaking empirical evidence. There's evidence I mentioned for...
But there's a formality to it, at least to proof.
So there's a difference between evidence and scientific evidence. Scientific evidence is a narrow, one particular area that's been very successful of kinds of evidence, but there's other kinds of evidence or reasons people could have.
Let me clarify why I asked you about science and religion. Both in the evolution of Homo sapiens are add-ons. They are human constructs, things we attach to ourselves and vice versa, obviously, in order to live more easily. Science is obviously that. Why do you think, now in your own specialty and domain, why do you think religion was obviously invented, discovered, and adopted by humans? A long time ago, not this monotheism to which you are referring. Why is religion
That's a very
useful?
Complex question, but I would think it has two. It's a huge question, but I would say two things. I think people do have a sense of the transcendent, and a sense of. So on one side, the philosophical side, they have a sense of the transcendent. They have a sense of moral value, and once you have the sense of moral value, if you see, let's say, evil in the world, people that commit evil often live better lives than those that do good, then it seems morality in many people's minds require that, the good ultimately are not worse off, at least, than the evil. Are better off. There's a sort of what happens to a person, but their moral character is eventually must coincide. So then you either get, just on a naturalistic basis, from those kind of things, you either get a heaven, a hell, or a reincarnation system. And then there's a sense of transcendent reality. That accounting for maybe the order you see in the world, that the world exists at all. But then there's a whole bunch more to religion than that, and there's a lot of then sociological explanations. Religion helps group cohesiveness, and we see that throughout the world. So then there's a whole bunch of sociological issues that arise, which is another big factor in religion. And then if you believe in revelation, then there can be, the revelatory side. But if you just give a naturalistic or merely philosophical account, I think those are the two big ones. And group cohesiveness from an evolutionary perspective is going to help the survival of the group.
But there you go. These things, these good things that you're enumerating could be contributed by a lover of science, all the way to wonderful mathematics, better engineering, how to build a city, how to stay away from danger, you name the place, okay? So the human urge to live more easily, safer, longer, is in the very beginning. And the earliest version, in my view at least, or knowledge of the history of man, the earliest way to put that urge to use, meaning to use nature, to live with nature, to live with the environment, was through religion. So I was curious to know whether, unlike many of my colleagues, you think that people in religion should fear science, and vice versa, people in science should fear religion. To me, they're all, in fact, human, religion being older. And a religion with science is definitely a much better add-on than a religion without science.
Right, well, I would agree. Religion with science is much better than religion.
Okay, I'm going to go to questions.
Please come up to the microphone and
Thanks, Bijan, for the questions.
keep your comments in the form of a question.
How you doing? So the question that I have is, I guess pretty much I kind of like going off the last thing. Given the fact that, okay, so the question being, couldn't mathematics itself be quote unquote God, right? And I'm putting in air quotes for a reason. Or couldn't knowledge itself be quote unquote God? Or couldn't sort of the idea of like what you were saying before in terms of like that transmutative nature of things in and of itself, or pattern itself that we sort of assign understanding to, couldn't that in and of itself be God? Like, does God necessarily have to be personification or anthropomorphication of what we see? Okay. Like, couldn't the intelligence itself be God?
Thank you. You want to tackle that?
Yeah, I'll tackle that. I think the kind of popular image you get of God as a God out there that's a very anthropomorphic image and molding things, etc. When I think of God, I think of it just as that, an underlying intelligence that grounds everything, so that the idea is that if you ask the question, what is, and I know you had comments about fundamental, when you go all the way back to reality, what do you find? Is reality ultimately impersonal? Is that the ultimate story? So is it just matter in motion, for instance? And then consciousness arises out of matter? So consciousness is sort of an epiphenomenon of the material? Or is that consciousness is the most fundamental? And then when you get consciousness, you get mind, usually goes along with it, and will, and intelligence, and mathematics has been the conceptualizations of that intelligence. That's one view of mathematics. And so in that conception of God, then it's really thinking that it's not an anthropomorphic conception of God out there, but a reality, a conscious reality that's underlying and sustaining everything. And so that it's a question of which route do you go at the very beginning of what's most fundamental, which leads you in these two different directions.
Let me also address your points. First of all, mathematics is not physics. Physics is nature. Physics is what happens. I like the Latin version of it, nature or natura, which is the personification of into a lady who gives birth to everything. So that is physics. Now, in the history of science, the description and the reasoning of these things that we see in nature came first, meaning was born out of this natura, as geometry. And that was a very cumbersome argument to teach, all the way to the school of Plato, which said he who cannot do geometry is not allowed to enter. Right. Very difficult. So then it was simplified. Algebra, trigonometry, or calculus. So in the beginning, geometric arguments from Newton. And so mathematics is a evolutionary process of simplifying the book of physics. That's what it is. So no, English is a much simpler language than say French and Latin. That's why English now has taken the world, taken over the world.
So I would disagree. Just kind of make a disagreement. I think in many cases, actually, the mathematics preceded the physics, like I mentioned, the complex numbers. So it wasn't actually useful in physics to quantum mechanics in the 1930s. But complex numbers, in fact, I think it goes back to the 17th, imaginary numbers in the development of the complex number system in the 18th and 19th century, like Cauchy's theorem.
I have to clarify just a second. Okay. Physics, the name for the discipline is new. It comes from the second half of the 1800s. Before that, it was called mechanics, and it is as old as the Greeks. Mm-hmm. And mechanics is the science of figures, bodies. Well, the ones that statically were described as geometry. Now these things, the pulleys, the ropes, the buildings, the making of the buildings was mechanics, the building of the ditches and the trenches and the roads. So mechanics is the original name for what I was talking about.
But the question was, could mathematics be God? So no. If you say physics preceded mathematics, are you saying physics could be God?
Einstein said that they're all God's laws. Okay. So that's the end to that.
Okay, next question.
I'm wondering, in considering these difficult questions, whether the panelists are really so sure of themselves as it appears. Why is it so difficult? People say, I don't really know. It seems obvious to me, given the dispute amongst you all, that no one really knows. But do you have doubts, or do you really think you're right, that you do know?
About what? About what?
About life, why things are the way they are.
We don't know.
Design or not.
That's for scientists. We don't know.
Yeah, well, I'm talking more of the other people who...
But I didn't understand the beginning of the question because I don't hear well. Would you speak slowly?
Yeah, I'm just wondering how people can be so sure of themselves about why things are the way they are, given the arguments and the disputes, and why people can't say, I don't know. It seems like a lot of these questions, people really don't know, but very few people
May I share with him a secret?
Yes.
Yeah, before this meeting started, we were having a round table in a back room there, and Dr. Narcissian, you brought up the fact that most people think they know more than they know.
Right.
I wanted to add to that most professors think they know more than they know, except Adrian. Okay? But so that's the way we are, okay? And very few, except those who are in a hurry to go home after a lecture or a conference, say, gee, I don't know. Excellent question, but I don't know. So it's a useful answer to many of these questions. But the urge to pursue the question, especially when it arrives so unexpectedly out of a honest audience, that courage is actually very valuable, and from me to my students, very, very important to teach, because most people do not get it, that they're actually free to question authority.
Thank you.
But if you can't propose some experiment that would prove you're wrong or right, make some prediction and say, we're going to do some experiment to show it comes out the way I think it does or doesn't do. How is that different than you mentioned
the work in physics theory is full of these examples.
Well, in physics it is, but in terms of your theory.
Sure. Here's the story of I predicted the evolution of speed in sports. I predicted it. That was in the spring of 2008. That was months before the Beijing Olympics. I predicted that the next winners in sprint and swim will be bigger. Okay? And with a mathematical formula, very simple, A equals B kind of formula. I submitted as a letter to Nature with a cover letter in which I said, dear editors, my colleagues, please publish this immediately, because in just 2 months from now, this will be shown to be correct. And they, of course, because I'm from engineering, decided not even to review my contribution. My contribution was on the rebound, published a few months later in the Journal of Experimental Biology in Cambridge, not a lightweight journal, meaning here are the facts, comparative biology journal. But in Beijing, in July, my prediction turned out to be correct. I did not predict the names of the winners, but I predicted their sizes and their speeds. You see?
But that's not proving a fundamental physical law, or
it is as proving in retrospect, meaning in hindsight, that everything that you brought up earlier with the insects and the so-called convergent evolution should be happening this way. That the bigger should be faster, not just waving your hands, but in accord with this precise formula. That is to predict that it was not questioned in the past is the proof that you are waiting.
No, the question: how many predictions did you make that didn't come true that we never heard about? The doctor already comes to the fact that has not happened yet.
Okay. Thank you. You want to say something about that? No.
I do. Do you have time? I just have a couple of comments. I really enjoyed this. It's wonderful. I haven't thought this much about these issues since college, and until the last election, of course. And I wanted to make a couple of comments, and they would raise questions regarding the existence of God. I think the gentleman in the lighter jacket, I was here late, so I don't really have all your names, mentioned that you can't test the existence of God, unless I got that wrong. And if that is true, then how can you describe God? That's one question. You might want to reference a show that Stephen Colbert had a few weeks ago or a few months ago, where Ricky Gervais was there, and he proposed the following thought experiment, which is that if humanity were wiped out, or all civilization were wiped out, would we recreate the same religions, or would we recreate the same physics and mathematics, which is more likely? And Colbert was, I think, stunned by that, which is impressive considering his deep religious beliefs and his mind. I also wanted to comment on what you mentioned about what I think is synchronicity, which is kind of parallel, parallel evolutionary appearances due to different processes. And I think that's an important thing to keep in mind. And the last thing I want to say is I did some research when I was a resident. I'm a pathologist by training. That did describe symmetries in biology, which I could discuss with you privately if you're interested, that speak to some very basic primal mathematical principles. I don't think it ever saw the light of day, but it was fascinating. Sorry.
Thank you.
A lot.
So, the two of you, I think, have questions.
Well, I think if I heard you right, you said if you can't test whether God exists, how can you describe God? Well, I mean, I can describe God, I have an idea of what consciousness is because I'm conscious, and I have an idea of what being an agent is and knowledge is. So I don't see where you'd have to test something to be able to describe it. I could describe on a very, very distant planet that is, what physicists would say, is outside our light cone, which means we'll never be able to determine whether it's there or not. I can describe there's a certain kind of being on the planet, let's say a unicorn, give you a description of the unicorn. So I can describe it without ever being able to test whether that's the case, or that there's extraterrestrial intelligence outside our light cone. So I don't see how the two are connected together. I think you'd have to have some sort of access to the properties you're using to describe the thing, but that doesn't require an ability to be able to test whether it exists or not.
Would you like to comment?
Sure, yeah. First, I'll just say that I like to think of God as a flying spaghetti monster. It's a big movement among evolutionary biologists to recast, religion of flying spaghetti monster. But with regard to sort of synchronicity and convergence, I mean, one of an interesting topic that's come up in evolutionary biology recently is trying to understand convergence not just from the framework of a common natural selective force, which is always how, since Darwin, it's been interpreted. When you see two things that look the same, you say, aha, they're under similar adaptive pressure. But now, I think with new tools, genomics, new tools in developmental biology and cell biology, we can start to understand the kind of canalization that is the molecular constraints at the molecular level that drive convergence in ways that may not be as related to adaptive pressure as we think.
Thank you. Any other questions?
It seems to me that all of the members of the panel, with the exception of Professor Bejan, really successfully avoided the topic at hand. And I think the topic at hand is, it says design in nature, is there design in nature? And what I heard from Professor Bejan was that nature designs itself, and it does it through the mechanism of evolution, which is underpinned by the law of physics. And that means, and that really is something which is, in its own way, post-creation or post-development in some way. So it still leaves open the question as to whether or not there was design or a designer. How did evolution, how did the law of physics come about?
Thank you. Who wants to tackle that?
Let me be very brief. In my latest book, The Physics of Life, the answer to your point is, I agree with what you bring up, is that evolution, which really means changing design with a perceivable, discernible direction over time, was on Earth and everywhere else from the beginning.
And I just want to follow up with, so I better understand what you were saying about nature design itself. Your example of the river basin.
Mm-hmm.
And I think of water flowing downhill.
Right.
And if the water flowing downhill wants to keep moving, then it keeps trying various ways of doing it. And it meets obstacles, but it adjusts. Did you describe that, or do you describe that as an evolutionary movement on the part of the water? Because it's the survival of...
It's an evolution of the flow architecture, and the river basin is just one part of it. It's the circuit executed by water in nature. First, there is the rain. The rain falls on the ground in the form of droplets. The droplets, while falling down, acquire a shape that tends to minimize drag. Okay, there we go. So that's the first. That's the call it the embryo that gives birth to the river basin. The river basin is the wet mud in the beginning. Then you have the rivulets, and then the hill slopes and the rivers, and so all the way to the delta. You forgot to mention delta, which is the river basin in reverse, just like the breathing in and breathing out. And then there is what happens to the water from the river basin, either evaporation from the ocean or from the Kalahari Desert in the case of the Okavango Delta. So, and then the evaporated humid air is lighter. It rises with undulating rivers. You see meandering rivers of plumes, which then circulate on the same world map as the winds more easily. So this is why I actually asked you about atonement. It's about not only the thing that you bring up, which is the river basin. It's about the river basin flowing together with everything else, with the so-called environment, or with the nature itself. So the physics is holistic. The laws of physics are obeyed by anything, everywhere and anytime. And that's why this discussion, this topic, I commend you for putting it together as a title, is extremely timely. And it is not about biology. It's not about technology evolution either. In fact, it's about everything that has evolving design.
Okay.
So maybe. So I'll just say, design for me is such a loaded word, right, as a scientist, because the last thing I want to say is that anything is designed, because I don't believe that. I don't think anything is designed. Design is something we impose after the fact on what we see around us. And it's because of our squirmy little mammalian brains doing the things. But it doesn't mean that there aren't some really extraordinary questions and big questions. So, for example, 13.8 billion years ago, the Big Bang, the universe was not the way it is now. It was extremely uniform, it was hot, it had almost no structure to it. Somehow, 13.8 billion years later, it's made structures out of itself capable of recognizing that fact. That's a big question, right? I mean, and it's a big scientific question, for me. And I think that's the more interesting thing. How did it happen? I agree, it's physics. But I don't know how to connect all the dots from 13.8 billion years ago to today. And I feel that sometimes, the fact that we impose this notion of design and form and shape and elegance and beauty on the world around us has been useful in some respects, but we don't know if that's the best thing to do for unearthing the deeper truths. I don't know. I really don't. So I just wanted to put that out there. I just wanted to say, say design to me, and I kind of go into a quivering mat, and I want to run out the door. Just to say that.
Let's see. Do you want to say something?
Well, not really. I mean, to me, it's like being a scientist. For me, it's not about figuring out the big questions and all this other kind of stuff. It's just, no, seriously, man. I just do it because it's fun. It's creative. It's like that. When we discovered it's like, I'm known for studying dinosaurs, and I can't stand dinosaurs. It's just, but, it's just a way to which, when we figured out what color dinosaurs were, it's not like we cared. We just wanted to see if we were clever enough to do it, and to figure out a way that we could use synchrotron radiation and stuff to be able to, do it. And that, so a lot of it is just that, because it gives us I view science as a mechanism for us to be able to, understand all the way from the most fundamental questions in the world to the lint of figuring out what color one kind of dinosaur was 130 million years ago. So that it allows us to be able to do that in a repeatable and fundamental way by, using mathematics, by using technology, and by asking the right questions. And it's just a way to approach the world in that way. So,
anybody else?
I can always contribute a question. Okay.
Oh, yes, you can ask another question.
It's there.
No, it's fine. I teach, so everybody can hear me. In terms of answering this question, wouldn't answering the question require some sort of multi-field understanding that, for the most part, well, that's two questions. So wouldn't it require some sort of multi-field understanding that we're just not really capable of in anyone's particular 90-year lifetime?
It's probably intractable. I mean, there's nothing wrong with that. I mean, as a
Yeah.
scientist, there's nothing wrong with saying, we can't do that, and I don't know that. So,
Yeah, because like one of the things I was thinking of was like, in terms of even just, for example, I was watching a documentary on Einstein, and it was a situation where like he ran into mathematics problems. And so it was a situation where like there was a race between him and another mathematician who was older than he was, and and he's trying to figure things out, and a lot of situations where I think, where like physics and science and psychology and all these other things. I teach a course, and I was just talking with this gentleman on the fact that Carl Jung, for example, knew a lot and consulted with people outside of his field, to answer a lot of different questions. And even as myself, as an English teacher, I often bring up things in terms of science and all these other things that I'm learning about, and constantly trying to say that, in terms of that understanding of like convergence, I think that would be necessary for understanding the underlying sort of intelligence that there is to creation. And then the second thing is going back to what you guys were initially talking about, in terms of the fact that, the dynamic is always changing. That, and going to your question, which is, isn't there always a situation where we don't know? Like at the end, I was reading something when they were saying at the edge of the chaos in the world is always creation, right? So isn't there always a situation where, and if we were ever to say this is God, then wouldn't that be the end of learning?
Okay, so that's your question. Okay.
Can I answer your question?
You can answer.
what time is it?
Your view of it is, in fact, in the right direction. First of all, design is basically a movie, not a sketch in a zoology book. Okay, that's the first thing. The second, there is no end to evolution. This speaks of the you call it the edge of chaos. I don't use the word chaos because it means I don't know anything, meaning I give up. It's like turbulence. So, but anyway, that's the good news, that there is always a flow architecture in the future that will be serving us better. And what you call it is really not only up to you, but depends on your upbringing. Some of us have gotten both religion and science. Others have gotten only the first. Others have only gotten the second. But every single one of us has the urge to live. I'm talking about. I included here my cat. The urge to live more easily, safer, longer, and all the rest. Okay.
But your question was, if there's a God, should we just stop questioning anything? Is that what you were?
And enjoy the fun experience of
living under Trump. Yeah. Yeah. No. But I think it's not about. I mean, I guess, right? It's going to mean, right? Depends, right? If you don't believe in God, right, then you're going to keep questioning. And if you do believe in God, you have a choice, right? And historically, many people who believe in God were also scientists and kept questioning the world around them and unveiling the majesty of whatever. I mean, it's just different motivation. Someone like me is not motivated that way. And even if you told me there is a God, I'd go, nah, not really. Nah, I'm just not going to go there.
Well, like and they ask me like every year. It's just like, what do I believe in? I say I believe in questions.
I think that's an excellent answer. I think that's an excellent answer.
One last comment and we stop.
I was just going to say, I think, and that's like some theory, a theory thing, and those who want to talk about the quantum creation of reality end up needing to hypothesize, like the mathematics of quantum mechanics, that it's not instantiated anywhere, it's just mathematics, and that somehow something, that mathematics is given being. So I'm just trying to clarify, I think that was your, and if you got to that final theory, whether it's a personal God or not, would questioning cease? Well, you might not be searching for the ultimate explanation anymore, but there'd be a lot of other things to explore.
I like
Thank
that.
you.
That's useful, I think.
Okay, thank you very much.
Unlike anything you've done before.
Yeah.